And so we can break any vector up into its components, which are directed along the x and y axis. And here's how we'll do it. If you have a vector northwest, you'll know that it has a north component and a westward component. And if you have a vector that's pointed up and right, you know that it has an upward component and a rightward component. So let's see how we do this. When we're generating components, the first thing you want to do is draw a diagram of the vector in question and label the magnitude of the vector and its direction. And around that vector, draw this rectangle that will be directed along the coordinate axes. The vector in question will go from corner to corner of that rectangle. Now, you want to make sure that the arrowheads show the direction which the vector is pointing. And you can draw in the components of the vector along the sides of the rectangle. Now, it doesn't matter what sides you use. Again, this vector is the same as this vector over here. They're the same because they're equal in magnitude and they're pointed in the same direction. This vector here is the same as this vector over here. Again, because their magnitudes are the same and because they're pointed in the same direction. And let's label our component vectors. If this is the vector s, then the vertical component will be called sy. This vertical component is also sy, because they're the same vector. The horizontal components will be s sub x, because these are the x components of the vector s. And we can use trigonometry to calculate the magnitudes of these vectors and the vector components. Let's take a look at how to do that. Let's redraw s over here. This is s, which equals 12 kilonewtons. And using trig is always easiest when you have a right angle triangle. So I'm going to draw sx over here and sy over here. The angle between them is 30 degrees, I believe. That's correct. And so let's generate the components sy and sx from the vector s and the vector s's orientation. Before we find those, though, let's examine the trigonometrical relationships between these sides, the sides of this triangle. So changing pen colors, let's go with red. If you look at this triangle, we have a right angle here. Why? Because the x and y directions are always going to be perpendicular to each other. And given that, s, this side over here, will be the hypotenuse of our triangle. And relative to this 30-degree angle, and only relative to that 30-degree angle, this, sy, is the opposite side. And sx is the adjacent side. Adjacent. Why? It's adjacent, or beside, the 30-degree angle. Sy is opposite the 30-degree angle. And so, if we examine the trigonometric relationships associated with the 30-degree angle here, we can say that sine 30 equals opposite over hypotenuse, which in this case equals sy, being the opposite side, over s, being the hypotenuse, right? So we do the straight substitution, opposite for sy, because in this case, sy is the opposite side. S for the hypotenuse, because in this case, again, s is the hypotenuse. And so, we can rearrange this to solve for sy. We already know the value of s. Sine 30 is just a decimal, which we can figure out on the calculator. And sy, rearranging for that, we can multiply both sides by s times s. These will cancel, and we'll end up with s sine 30 being equal to sy. Or, we can turn that around, sy equaling s sine 30. Similarly, this is a semicolon, not a J. Highlight that. Similarly, if we look at the cos of 30 degrees, that will equal the adjacent side to the 30-degree angle divided by the hypotenuse of the triangle. And so, filling in the specifics of this triangle, the adjacent side to the 30-degree angle is sx, the hypotenuse is s, and similarly, multiplying both sides by s to solve for sx. This will cancel because we're multiplying by a number and then dividing by it. We can say that sx equals s cos 30 degrees. Now, don't get too hung up on this idea that x involves cos. In this case, that's true. Y involves the sine of this angle. But don't get too caught up on that, because you might not be given that angle. For instance, you could have potentially, and just as easily, drawn this triangle in order to find the components of s. This here is sy. Oh, sorry, that's not true. This is sx over here. Sx, and this is sy. And if you're using this triangle, sx is now the opposite side, and sy is the adjacent side, and this is still the hypotenuse. And if you are calculating sx from this triangle, then sx would equal s sine 60, and sy would equal s cos 60. So, depending on the angle you start with, your s and y may be oriented differently toward that angle, and you will be required to use a different trig function. And so, what's important is that you pay attention to how the components are oriented with regard to the angle that you're using, not just blindly memorizing this formula that says sy equals s sine 30. Take a look at the relationship between the components and the angle that you have. Now, in some situations, like this one, the x and y axes are less important. In this case, this box is sitting on a ramp, and we want to know if it's going to move along the ramp. This is basically the only direction it could move in, unless it was rocket propelled. But we want to know if this is going to slide down the ramp or slide up the ramp based on whatever forces are acting upon it. And that being the case, what we're most interested in is not the x and y, but this turned axis, the x prime axis and the y prime axis. Why is that? Because if it's moving in the x prime, then it's going to move. And so in this case, we have Fg, which is the force due to gravity, which is equal to mg, and we'll need to figure out components of this in the x prime and y prime directions, right? If we figure out the x prime component of this, and then take into account any other forces like friction or some push that's happening, we can then figure out if this will slide down the ramp by itself or not. And so the frictional force that we find will be related to the normal force, which we'll talk about later, which is going to be equal in this case to the y prime component of gravity. So here's Fg y prime, and here's Fg x prime. And in this case, it's the axes x prime and y prime that are most interesting, because these are the directions, or x prime is the direction in which any motion would be happening if it were to happen. And so Fp and Fn, Fp you could call the driving force, Fn being the y prime component, which is equal to the normal force, which is the force that holds this on the surface of the ramp, not allowing it to fall through. Now, when you're adding vectors, we've been taking them apart. When you're adding vectors, what you need to do first is, in fact, find their components. So if we're adding vectors a and b and c, the resultant will be this vector d. And we can do this graphically by taking a, drawing it to scale with its length proportional to its magnitude at the angle that it should be at. Similarly, b with its length proportional to its magnitude at whichever angle it should be at, and c with its length proportional to its magnitude. If those are all drawn to scale and in the proper directions, then we can add these vectors tip to tail, a plus b plus c, and the resultant vector, the total vector, d, will just be the straight line path between where a starts and where c finishes. So we can do that, that's fine. Now, it's really difficult to be very accurate doing a scale drawing. So you may choose to do this algebraically, and the way to do this is to break each vector into components in x and y in this case. X component of a, x component of y, x component of b, y component of b, x component of c, y component of c. Then what we can do is take all the x components here, here, and here, and add them up for total x. The total x going from very beginning to very end, and add the y components, a y plus by plus cy, to find a total y. And those total x and total y will also add up to d. We can figure out the direction of d, this theta here by recognizing that this total y, in this case the total y, is opposite to d, and this total x, this side over here, is adjacent to the angle, and so dy divided by dx is the opposite side over the adjacent side. Remember that the tan of an angle equals opposite over adjacent. So in this case, the tan of this angle equals dy over dx. So whatever our dy is, divide by whatever our dx is, we'll get some number, and we can inverse tan that, or tan to the power of -1. We can untan that to get the angle theta, which is right here. Now, what's important here is that we keep organized. And so what works best often is to set up a table to keep track of the x components and the y components, have them add all up, and we can put those together into a resultant vector at the end. So here, in this case, in the example here, we have A, and if we define the angle lowercase a, then AY is the vector A times the sine of lowercase a. And AX is equal to the vector A, the length of the vector A, multiplied by the cos of small a. And if we define a vector B, an angle B, then the x component of B is equal to the vector B, that is its length, times the cos of little b, and the y component of B is equal to the length of the vector B times the sine of small b. The same can be said for C. And when we want to find D then, we can find dx by adding up all of the x components of A and B and C. And if we want to find dy, that's just equal to the sum of the y components of A, B, and C, AY plus BY plus CY. So let's do that. Let's do that in practice. Here's an example. Let's add the following vectors. These are different A, B's, and C's than in the previous example. A is a 30 Newton vector directed at 45 degrees on the Cartesian plane. 45 degrees would be right here. And the vector B would be 45 newtons at 90, so straight up. And vector C would be 70 newtons, so fairly long, and directed at an angle of 300 degrees. Here's 0, 90, 180, 270. So C might look something like that. And let's then break these vectors into their x and y components, add up the x components for the total x, add up the y components for the total y, and come up with a resultant vector D, that is the sum of A and B and C. And so what we'll do is look at the vector A. It's 30 newtons at an angle of 45 degrees. here is AY, and here's AX. Now, this 45, relative to the 45, AY is the opposite side, AX is the adjacent side, and A is the hypotenuse. So I can write that in. This is the opposite side. This is the adjacent side. Adjacent side. This is the hypotenuse. Now, we can say that sine 45 equals opposite over adjacent, equals opposite over hypotenuse, which will equal AY over A. We know A is 30 newtons. We know that sine 45 is just a number. And AY then is an unknown, which we can solve for. So we can say that AY, I'm going to multiply both sides by A. Cancel over here. AY will equal A sine 45 degrees. Similarly, using the same method but with cos, AX will equal A cos 45 degrees. Now, in this case, because A is 30, AY will equal 21.21 newtons, and AX will also equal 21.21 newtons. Now let's look at the directions of these vectors. AX is in the positive x direction, so that's positive. AY is pointing up, so this is also positive. All right, so let's make our chart here. Let's make it over on this side. So we are x and our y, and for the vector A, the x component will be 21.21 newtons, and the y component will also be positive 21.21 newtons. For vector B, let's imagine that was straight up and down. Vector B, which is at 90 degrees, is 45 newtons. And so, because it's straight up and down, for vector B will have no x component and a y component of 45 newtons. Now with vector C, let's take a look at that. This is for A, this is for B. For vector C, let's draw out the Cartesian plane to make things a little bit clearer. So we have y-axis and our x-axis. Our C vector will be located something like this. And so, just for demo purposes, I'm going to define this angle here. Right? So this is vector C, this is cy, and this is cx. Before we go any further, I'll point out, look, cy is pointing downwards. That means that this, the y component of C, will be a negative number. The x component of C is pointed to the right, so that's going to be positive, as was this. Okay, so just by looking here, we can tell this is going to be negative. Whatever number, what we're going to end up for C with for cy, a value of cy, is the length of this side. In terms of direction, because it's pointing down, cy is going to be negative. All right? So C has a value of 70 newtons. And let's look at Cx first. Cx will equal, because it's opposite the 30-degree angle, will equal C times the sine of 30 degrees. C times 30 the sine of 30 is 35 newtons. Cy, because Cy is adjacent to the 30-degree angle, Cy will be equal to C cos 30, which will equal 60.62 newtons. Cy, again, will be negative, not because this comes out with a negative number, but because of the orientation of Cy. The 60.62 newtons that we came up with is just the length of that side. The negative comes from its orientation. It's pointed down, and as per convention, down is the negative y direction. So Cx, 35 degrees, 35 newtons. Cy, 60.62 newtons. Now, the resultant then, the x component of the resultant will just be the sum of all the x components, which will equal 56.21 newtons. The y component of the resultant will equal 21.21 plus 45 newtons minus 60.62 newtons, which will give us a value of 5.59 newtons. And so what we're going to do is, because we have the x component and a y component, we can put those together using Pythagorean theorem, and then we can use trig to find the angle that this vector is oriented at, and then we'll have both the magnitude and the direction of the resultant vector, which means we'll be done. All right, so let's do that then. We have, for the vector d, we have an x component of 56.21 newtons and a y component of 5.59 newtons. Now this vector diagram is not to scale, obviously, because this is not 10 times as long as this. This is dx, this is dy. And here's the angle I'll choose to look at. It's the angle off of the positive x-axis. And so we can say that tan theta equals 5.59 newtons divided by 56.21 newtons, which equals 0.099. This is longer than 0.99. What I'm going to do is write it here, but I'm going to use all of the digits to calculate theta. If I inverse tan this, we can find the angle that gives us a tan value of 0.099, and that angle is 5.68 degrees. And so our resultant vector then, the result of adding a and b and c, which is the vector d, we've called it, is equal to, oh wait, we haven't done this yet, d. According to Pythagorean theorem, the length of d will equal 56.21 newtons squared plus 5.59 newtons squared, and d will equal the square root of that. C squared equals a squared plus b squared, and if we take the square root of c squared, in this case it's called d, then it equals the square root of the squares of the other two sides, of the sum of the squares of the other two sides. Doing that, we get a magnitude of 56.49 newtons. And so D, 56.49 newtons. We have the angle, we have the magnitude, D equals 56.49 newtons in the direction 5.68 degrees. Now in this case, we did find the angle off of the positive x-axis, which is where angles are reported from. In other cases, you may have found an angle that is from the, say, positive y-axis, and that's not the angle then that you would report. In this case, we're going to report the angle that we found because it's off of the positive x-axis. If you were to find, for instance, an angle up here, this theta, you wouldn't report theta in your final answer. You'd report, again, the angle from the positive x-axis. If you found theta, you'd report 90 degrees plus theta. Similarly, if you found some angle here, call this theta 2, you wouldn't report theta 2 as you found it, you'd report, again, from the positive x-axis. And for some practice adding vectors, in chapter 1, there are questions 1.29, 30, 31, 41, and 43, which are available for you to practice on. I will make those available, the relevant pages available on Blackboard, and I hope you found this at least informative, perhaps interesting.